So when scientists started to generate these line spectra, for example, for hydrogen, like we can see here, um, the next thing that they wanted to do was they wanted to try and explain why this is happening. Like, how do we explain these unique line spectra for each of the individual atoms? And we have this guy here, his name is Niels Bohr. He was a Danish physicist, and he came up with a theory to explain um, why hydrogen gives a spectra, something like this, to explain this like occurrence and phenomena that we see happening. And he explained the line spectra for hydrogen. Now, if we think about hydrogen as well, hydrogen is the first element on the periodic table. So essentially it has a nucleus and then it has one electron in its outer shell. So it's relatively simple in comparison to some of the other um, elements or atoms that are on the periodic table. So Niels Bohr decided to try and explain this. So just if we kind of think about, first of all, like how this spectra is generated, just to kind of refresh our memory. So imagine we have a tube, let's say something like this. And this is a discharge tube. And what we have is we're passing, and this just represents, so we're passing energy through this discharge tube. And inside it, then we have atoms of hydrogen, for example, that are in a gas state. So imagine these blue dots here represent hydrogen atoms. So what happens is so there's just hydrogen in here, we pass an electric current through this discharge tube, and what happens is the atoms of hydrogen start to give off radiation. Okay, and they start to give off light or give off radiation. Now, if we pass this light through a prism, something like this, what's going to happen is it's going to split up the light. So you have one, let's say, wave, you have light passing in this direction, but it's made up of a number of different wavelengths all mixed in together. Now what happens is you put that through a prism and it diffracts, it splits them up. So imagine then this is our background, similar to this here. And what happens is the light gets split up, and you might get a band here. Okay, that might be that red band. Then you might get another band here. Then you get your band here and your band here, like so. So essentially what happens is the light gets split up, and the different individual wavelengths are split up, and then they appear on this background. And this is like what a line spectra is. Now, what's the difference in these different colors of light? Well, the difference is the wavelength. So if we imagine light as a wave, for example, if we measure the distance from crest to crest, we have what's known as the wavelength. And depending on the wavelength, it will determine how much the light is bent when it passes through a prism. So it gets bent at different amounts depending on the wavelength. So as a result of that, if you like, it's a way that we can split up light. Now, when we put hydrogen, for example, and other elements through, when we put them in a discharge tube, turn them into a gas, put electricity through the energy, and get the atoms to emit light, and then you pass it to a spectrum, what you do is you get this unique spectrum, like exactly what we see up here. So this is the line spectrum for hydrogen. So really what we want to do, and what Neil is trying to do, is to explain why this happens. Like what's the mechanism, or what's the explanation around this. So if we have a look here then at this. So this here represents an atom of hydrogen, for example. And hydrogen is very simple in comparison to the other elements. So it essentially has a nucleus. It has a proton in its nucleus. And then it has one electron. And this one electron, kind of, if you like, one way to think about it is that it orbits around the nucleus like so. Now, the energy of the electron in the hydrogen atom is restricted to a certain value, or it's quantized. So if we take, for example, elemental hydrogen, so its one electron will generally hang out in this space here, closest to the nucleus. And we can another way we can think about this is an energy level. So we can call this energy level n is equal to 1. So when the electron is in this energy level, it has a definite amount of energy. It has a fixed amount of energy. And that fixed amount of energy, you can think about it, it's what's known as it's quantized. So Q U A N T I S E D. So the energy is quantized. So in order for, like for example, when the electron is in this first energy level, the electron has a fixed amount of energy. If it doesn't have that energy, it won't be able to hang out, let's say, within this space. And the way to think about it is these energy levels, they move out from the nucleus, further and further and further out from the nucleus. And the energy is fixed, or it's what's known as quantized. So imagine this is your atom of hydrogen, and it's not receiving any extra energy from the environment around it. So this is it in its ground state. So essentially the electron will be in this first energy level beside the nucleus. So it's not being excited, it's not being given any energy, it's just hanging out here, this one electron, in this lower energy level, in the n is equal to 1 energy level. So we have these, what are known as energy levels. And this is another way that we can represent these energy levels. We have this n is equal to 1, so this is the first energy level. And the first energy level is the level, let's say, closest to the nucleus. Like so, like this is, if you're to look at the nucleus of an atom, this space here that's closest to the nucleus is the first energy level, and it's represented here, n is equal to 1. Now, as we can see, as the nucleus moves as the electron moves further and further away from the nucleus, its energy value increases. So we can see here, as we go up the energy levels, the amount of energy the electron has increases, and these energy levels go up and up and up, but go up and up and up, and we can go right up into infinity, for example. So basically what happens is the electron can move, let's say it can move to the next energy level, move to the next energy level, and move to another energy level. Now these energy levels are very fixed, as in they're very exact. So the electron can only be in an energy level, it can't be somewhere in between the two energy levels. So it's either, let's say, in the n is equal to 1 energy level, or it's in the n is equal to 2 energy level, but it can't be anywhere in between. Now, how does the electron move, let's say, if it's in this first energy level, how does it move up here to the second n is equal to 2 energy level? Well, what has to happen is it has to receive energy, or it has to be excited. So in the discharge tube, for example, the energy is supplied by the current that's passing through. So what will happen is this energy will be picked up by the atoms of hydrogen within the discharge tube. It'll excite the electron, and the electron will jump up to the next energy level. Now, remember that these energy levels contain a very fixed amount of, like the electron needs a very exact amount of energy in order to be able to jump up to this energy level. If it doesn't get that exact amount of energy, it won't move up to the energy level. So each energy level has a very specific energy value associated with it. When an electron receives that very specific energy value, then what will happen is it will actually move, it'll get excited, and it'll move up into that energy level. Now what happens is when the electron moves up here, so let's say this is our electron here, okay, so we have our electron, it moves up into this higher energy level, it gets this exact amount of energy, okay, so it receives this exact amount of energy. Now when it's up here, it's actually unstable. So what's going to happen is it's going to, after a period of time, it's going to drop back down again, back down to the ground state. Now, so what's happened is, a way to think about it is, so the energy has come in, the electron has absorbed the energy, it has absorbed this exact amount of energy from here to here, it's been excited, it moves up to this higher energy level, and then it stays there for a period of time, and then it drops back down to its original its original energy level. Now, when it drops back down, it gives off energy, or it gives off a wavelength of light. And that wavelength of light is equal to the energy difference between this first level and the level that it jumps back up into. So the amount of energy that's given off when the electron becomes excited and then drops back down to its original energy level is equal to the amount of energy. It's equal to the energy difference between these two energy levels. And this can be represented in a formula mathematically. We can say, so E2 minus E1 is equal to H times the frequency. So what does that mean? So for example, E2 in this case is going to be the energy level associated with this energy level. E1 is the energy value associated with this energy level. So what you do is you subtract the two of them from each other. The difference is going to be equal to the wavelength, or the energy that is emitted when the electron moves up into this higher energy level and comes back down again. And this can be represented like this in a formula. And what we have here, so this here is the frequency. So the frequency, a way to kind of think about that is you have wavelengths of light and they're passing a particular point like so. So the more of these waves that pass this point every time is what's known as the frequency. And this value here, H, is equal to what's known as Planck's constant. So it's just a constant that's used. So, but essentially just what you really kind of need to understand is that the energy that's given off is equal to the difference between the two energy levels. Now what can happen is you can get an electron that moves from this N1 up to N3, then falls back down again, and it'll give off a wavelength of light that's equal to the difference. It has energy equal to the difference between these two energy levels. Now what's important as well is that the electron will only move from this lower energy level to the next energy level if it receives the exact amount of energy that it needs. If there's, let's say, a little bit too much energy or not enough energy, it won't move up to this higher energy level. Like, it doesn't just move up halfway or move up halfway between here. It has to receive an exact amount of energy. And these numbers here are what are known as the principal quantum numbers. So principal quantum numbers. And each of these quantum numbers or energy levels have a very specific energy value associated with them. And the way that they are is like, so n is equal to the 1. So the closer the electron is to the nucleus, so the n is equal to 1 energy level. This is the least, the electron has the least amount of energy. But as you move up higher and higher and higher, the energy value that the electron must hold in order to be up in this level increases. So what we need to kind of try and figure out then is, like, how do these energy levels and the electrons being excited and dropping back down and giving off energy, how do they relate to these specific bands of energy, or these specific bands that we see which show up on a line spectrum for hydrogen? Another thing to think about as well is that when the electron is in this, in this state, for example, where it hasn't been excited, it's what's known as the ground state. And then when the electron gets excited, it's what's known as its excited state. So it moves from ground state to excited state and then back down to ground state, and then it gives off this specific wavelength of light. Now generally what happens is, when you get, so for example, when one of these hydrogen atom electrons, when it moves from this first energy level up to the second energy level, and then it moves back down to back down to the first energy level, it gives off a wavelength of light that's associated with the ultraviolet range. Okay, so it has that very specific ultraviolet range of radiation that it gives off. Also, equally as well, sometimes what you can get is you can get an electron that starts off, let's say, it starts off here, gets excited, and it goes up to n is equal to 3, and then it drops back down to the ground state, and it gives off energy. And again, generally when electrons get excited up into n is equal to 2 or n is equal to 3, and then they come back down to the n is equal to 1, they'll give off light that's a wavelength of light, or electromagnetic radiation, or another way to think about it is a specific amount of energy that's associated with the ultraviolet electromagnetic spectrum. Now, if we think about, so if we have a look here then, so here what we have is what's known as the Balmer series. So the Balmer series. And the Balmer series is really this visible line light spectrum for hydrogen that we're talking about here. I'll just put it down here. So how does this, so again what we're trying to get back to, or what Niels Bohr was trying to explain, is how do we account for this spectra being formed. So what happens exactly then in relation to the formation of these what's known as the Balmer series, or the Balmer series line spectrum for hydrogen, and how does that link into the energy levels, these energy levels that we've been talking about. So a way to think about it then, all of these lines are generated when electrons move up into an energy level and fall back down, and they give off a wavelength of light. And each of these lines are associated with that with electrons being excited, moving up into a higher energy level, and then moving back down, and then they give off a very specific wavelength of light. Now, in relation to the Balmer series, all the lines in the Balmer series are due to electrons dropping from higher energy levels down to the second energy level. So if we think about our, maybe I might just bring this down as well. This might make it a bit easier to kind of understand it. So here we have our atom of hydrogen, and it's one electron. So this first level here is n is equal to 1. This ring here, where this is n is equal to 2, this is n is equal to 3, and then so on and so forth. You can keep having higher and higher energy levels, and this can be just represented like this. Okay, just like this kind of a diagram here. So essentially, it just represents the energy levels. So what happens is the electron gets excited. Now with the Balmer series, what happens is all of the lines that are accounted for, they come from the electron being excited up into these different energy levels, and then falling back down into the n is equal to 2 energy level, which is this level here. So what can happen is the electron can become excited from here. It can go all the way up to here, for example, and instead of coming all the way straight back down, it can come down to this level first, give off energy, then it can come back down to this level, give off energy, etc. Or it can just go straight up to this level and then fall straight back down to this level and give off energy as well. So they do kind of slightly vary as well in relation to how they come back down and drop back down. So then, and that's what happens. Like, so if we have a look here, so this red line that's generated on the Balmer series, or the line spectrum, what's happening is, how is this red line produced? What happens is you get an electron that moves up into the n is equal to 3 energy level, and then it falls down to the n is equal to 2. It gives off this radiation of light. That light passes through a prism, and it's bent at a very specific angle, and it shows up as a red line in a very specific position, let's say on your spectra. So how do we account for, let's say, these other colors then that are being produced? Well, what's happened is, so this color here, the electron moves up into the 6th energy level, n is equal to 6, and then it comes back down to the 2nd energy level. And when it comes back down to the 2nd energy level, it gives off that, gives off the very specific radiation of light. So same as what happens here. So we get the electron excited up to this energy level, and then what happens is it falls back down and it gives off this band of light. This electron moves up to this energy level, moves back down to the n is equal to 2, and it gives off this very specific band of light. So that's how the energy levels are linked in, let's say, with the line spectra. So for atoms then, so this is like how Niels Bohr then, he linked in, or he explained, let's say, mathematically how the line spectra is formed and how that relates to the atom of hydrogen and the subatomic particle, the electron, and then the wavelengths of light that are absorbed and emitted by these particular electrons in order to get them up into these very specific energy levels. Now this idea, or this Niels Bohr's model for simple elements like hydrogen, it works very well. Like, it can be used to explain it very well. Now the problem is when you start to move up the periodic table and you start getting atoms with more than one electron, then it starts to just get a little bit more complicated. And what we'll do is we'll kind of talk about that a little bit more in the next video. So that's really kind of just an introduction into the link between, well, it's talking about line spectra, which are these line spectras, and then linking it in with energy levels on electrons or on atoms, and then how these two kind of tie in together and how they explain, these formations of line spectra that you see. So hopefully that makes sense. So thank you for listening, and we will talk more about this then in the next lesson.